The prime number triangle, order in the chaos of numbers. How a simple structure might help us understand the appearance of prime numbers. Prime numbers have fascinated humanity for thousands of years. They are considered the building blocks of all whole numbers, and yet their distribution seems arbitrary, almost chaotic. Great mathematicians such as Euler, Riemann, or Erdős have gained deep insights into prime numbers, but a complete understanding of their distribution has remained elusive to this day. Prime numbers still appear as if randomly scattered along the number line. But what if there were a structure that could bring order to these points? A new way of representation that not only visualizes them, but also allows predictions. That is exactly what the so-called prime number triangle promises. The prime number triangle and dyadic levels. The prime number triangle arranges numbers in a structure that resembles a right-angled triangle. Its horizontal division is made into so-called dyadic levels. Each of these levels starts at a multiple of 2 and extends to the next higher multiple of 2. These multiples are also known as powers of 2. For example, 2 to the power of 0 is 1, 2 to the power of 1 is 2, 2 to the power of 2 is 4, 2 to the power of 3 is 8, and so on. In this way, the space of numbers is divided into ever broader horizontal sections. First, just the 1, then 2 to 3, then 4 to 7, then 8 to 15, and so on. Beneath these numbers, vertically, are the prime factors from which every whole number can be constructed. According to the rules of divisibility, every number can be uniquely factored into primes. This fundamental fact forms the basis of the prime number triangle. The dyadic levels are not only useful for giving an overview, but also for creating structure. Certain mathematical properties apply within each level. All numbers in a level are less than the largest number in that row. This means that the factors that make up these numbers are all smaller than this highest number, and the factors themselves, appearing in order, are simply the prime numbers. Thus, each dyadic level becomes a grid. It shows the number space of a power of 2, the prime factors of each number within that space, and how new prime numbers enter, step by step. This structure is based on two things. First, the division into powers of 2. Second, the growing sequence of prime numbers, which appear as rules of divisibility within each level. Structure through triplets. All prime numbers greater than 3 lie at the edges of so-called three-number blocks, triplets, always at the first or third position. A few examples: 5, 6, 7, 11, 12, 13, 17, 18, 19, 23, 24, 25. Only the two edge numbers in such triplets, the first and the third, can be primes. This simple observation makes it possible to lay a grid structure over the number line. We segment the numbers into consecutive triplets and systematically look at which of them can contain prime numbers. Some of these triplets contain 1 or 2 primes, others none at all. But what distinguishes them? The exclusion of primes by prime factors. A triplet contains no prime number if both edge numbers are divisible by smaller primes. To recognize this, it is enough to systematically check whether the edge numbers are multiples of smaller primes. Let's look at this concretely. In the range of numbers from 1 to 4, that is 2 to the power of 2, we find the triplet 5, 6, 7. Here, 5 and 7 are primes. The triplet is therefore complete. In the range up to 8, 2 to the power of 3, we have the triplet 11, 12, 13. Here too, 11 and 13 are primes. In the range up to 16, 2 to the power of 4, there are several triplets, 17, 18, 19, or 23, 24, 25. We see that 25 is not a candidate for a prime, as it is the product of 5 times 5. And at the end of the row, the triplet 29, 30, 31. In the range up to 32, 2 to the power of 5, we see 30, 46, 37. 35 is 5 times 7, so not a prime. 37 is a prime. 41, 42, 43. 41 and 43 are primes. 47, 48, 49. 47 is a prime. 49 is 7 times 7. 53, 54, 55. 53 is a prime. 55 is divisible by 5 and 11. 59, 60, 61. 59 and 61 are primes. A pattern becomes visible. The The largest prime factor that prevents a number from being a prime is smaller than the square root of the highest number in the row. The prime factor exclusion conjecture, in simple terms, in a number range from 1 up to 2 to the power of n, all primes fall out of the triplets if they are divisible by a prime number smaller than the square root of the highest number in that row. The triplets, therefore, already rule out half of all numbers as prime candidates. A targeted check of prime factors shows the gaps, where there can be no more primes. It is not necessary to check every number, just the edge numbers of the triplets, in structured form. Comparison with Pascal's triangle. Just as Pascal's triangle visualizes combinatorics, the prime number triangle could illustrate the distribution of prime numbers. Both use geometric arrangement to make deep mathematical principles visible, one with binomial coefficients, the other with the factorization structure of whole numbers. Meaning and outlook, this perspective demystifies prime numbers to some extent. They appear less random and more like part of a geometric pattern. This could have consequences for algorithmic number theory, for prime sieves, and perhaps even for cryptographic methods. But for now, the prime number triangle invites us to explore. It is a tool that is useful both for popular science explanations and for algorithmic research. An invitation to reflect. Is the prime number triangle a new Pascal's triangle for number theory, or merely an interesting visualization with no deeper consequences? That remains to be seen. But even now, one thing is clear. Structure is possible, even in the seeming chaos of prime numbers.